In this video, I'll help you solve the ALEKS problem called finding the minimum uncertainty in a position or velocity measurement. There are two versions of this problem. One version has you find the uncertainty in a position measurement. The other version of the problem has you finding the uncertainty in velocity. I'm going to walk you through this particular version of the problem, which is asking us to calculate the uncertainty in velocity. It's actually the harder of the two, and I'm also going to talk with you about how you would go about solving the other type of problem where you're finding uncertainty in position. No matter which variation of the problem you're looking at, these are the two equations that you need to use. Delta x times delta p is greater than or equal to h over 4 pi, and then also delta p equals m delta v. I'm going to talk about these equations as we use them while we're solving this problem. So the first thing that we're going to want to do is actually read the problem and take a look at what information is important and what ALEKS is asking us to do. So this is telling us that we have an atom. It has a radius of 154 picometers, and it has electrons in it, and the electron's velocity or the electron speed is 1.8 times 10 to the 8th meters per second. It wants us to calculate the uncertainty in the speed of the electron. So one thing that you definitely need to look out for when you're solving this problem is to pay attention to what ALEKS is actually focusing on in the problem. It is always going to give you information about a particular atom. Sometimes it wants you to find the uncertainty in the atom's position, or velocity, and sometimes it wants you to find the uncertainty in the electron. So it is a pretty big difference in the way that we approach the problem. This one is asking me to find the uncertainty in the speed of the electron. So I need to keep that in mind as I'm solving the problem. Okay, so I have been given the information that I've been given, this 1.8 times 10 to the 8th meters per second. That is the actual velocity of this particular electron. So this is the velocity. It is not the uncertainty in the speed or uncertainty in the velocity. It's just the straight up velocity, 1.8 times 10 to the 8th. And notice that that doesn't belong in any of these equations at all, although it is a number that we have to use. The other thing that's been given to us is the radius of this particular atom, which is actually really important. In this problem, it's telling us that we've got this particular atom that has a radius of 154 picometers, and the electron is somewhere inside this radius. So the electron in this area, its position is somewhere in this area, and we're going to refer to that as its uncertainty in position, meaning that we know that it's in there somewhere, but we're not certain about where exactly it is. Now, the uncertainty of the position of the electron is across this whole entire spherical atom, which has a diameter of 2 times the radius. So the uncertainty in this particular position of the electron in this atom is 2 times the radius of the atom. The radius of the atom is 154 picometers, which is 308. 2 times 154 picometers gives us a radius of 308 picometers. And I need to, if we pay attention to this right here, I need to express that in units of meters, not picometers. So 308 picometers is going to be 308 times 10 to the negative 12 meters. If you're working on this problem, I'm assuming that you're pretty comfortable with unit conversions inside the metric system, so I'm not going to go into a lot of detail on that. So this gives me the uncertainty in the position of the electron, and since this portion of the equation are all constants, h is Planck's constant, pi is a constant, I can now use this equation to solve for the uncertainty in the momentum, which is what I'm going to do next. The uncertainty in the momentum, I'm just going to do some algebraic rearrangement here, is equal to Planck's constant over 4 pi delta x. Planck's constant is 6.626 times 10 to the negative 34. The units of Planck's constant are joules times seconds, and that is going to be over 4 pi times my uncertainty in the position, which is 308 times 10 to the negative 12 meters. Now, joules is a unit of units. A joule is a kilogram meters squared over seconds squared. And what I'm actually going to do here, I'm going to spread that out a little bit, is I'm going to write the units, I'm going to write out the units of the joule. So kilograms meters squared over second squared. second. It's going to make it a little bit easier for us to see the units as we're working on this problem. So next thing that I'm going to do is actually carry out this math and solve for delta P. Delta P is greater than or equal to Planck's constant, 6.626 times 10 to the negative 34, divided by 4 pi times 308 times 10 to the negative 12. That gives me an uncertainty in momentum of 1.71 times 10 to the negative 25. For my units, the meter is going to cancel, the seconds are going to cancel a little bit, and I'm going to have a unit here of kilogram meter over second. Now let's take a minute to think about what are we even trying to do here. We're trying to calculate the uncertainty in speed, which is this term in this equation right here. We just figured out the value of delta P, and we know the mass. We can look that up. So we do have the ability to calculate the uncertainty and the speed. Now here's another, this is where you need to be careful about what ALEKS is asking you to focus on, because ALEKS is giving you information about an atom, lead, but it's actually asking us to focus on the speed of the electron. So in this equation where we're plugging in mass, we're plugging in the mass of the electron. We're not plugging in the mass of the lead. There are some versions of the problem where ALEKS is asking you to focus on the atom, in which case you would be plugging in the mass of the atom, not the mass of the electron. So just pay attention to what ALEKS is asking you to do. We are now going to use this equation to calculate the uncertainty in the speed. Delta V is delta P over M. Delta P is 1.71 times 10 to the negative 25. I got to move this down a little bit, and the units are kilograms meters over seconds, and that's going to be divided by the mass of the electron, which is, I believe, is 9.1 times 10 to the negative 31 kilograms. You can just look that up. I'm going to double check really quick and make sure that I have that number correct, and take a look at how our units of kilograms cancel out. Let's carry out the math on this. Our answer from the previous calculation divided by 9.1 times 10 to the negative 31 is going to give me a delta V of 188,126 meters per second. Now, we're not quite done with the problem yet. We did calculate the uncertainty and speed. ALEKS wants you to write your answer as a percentage of the average speed. So we can't just give it the uncertainty. It wants it as a percentage of the average speed. And this is where we're going to use this number right here, the average speed, which was given to us in the problem. So to do that, we're going to take our uncertainty and we're going to divide it by the actual average speed. The uncertainty, which was 1.88 times 10 to the 1.88 times 10 to the 5 over the actual average speed, which is 1.8 times 10 to the 8. And it does want this, I need to make some more room here. It wants this as a percentage, which means that answer that we get, we're going to multiply it by 100. And so that is going to give us 1.8 times 10 to the 8, multiply by 100. It's going to give us 0.10% to two significant figures. And that's the answer for this problem. Now, the other version of the problem, obviously, the other variation of the problem is where you're calculating uncertainty in position. So this is the term that you're calculating. In the other version of the problem, ALEKS is going to give you the uncertainty in speed. It's actually going to give you the speed and the percentage. So you're going to use this equation right here. You're going to use your percentage and your actual speed to calculate delta V. You're going to plug the delta V and the mass into this equation and solve for delta P. And then you're going to plug delta P into this equation. You know H and 4 pi, they're both constants, so that you can solve for delta X. And in the other version of the problem, ALEKS has you do this type of thing at the end as well, where it doesn't want you to actually express delta X. It wants you to express delta X in terms of some other distance. like the distance of a box or something along those lines, to put it back into a percentage. Or at least that's the versions of the problem that I've seen. Good luck with this problem. It is pretty tricky. Just take your time, be patient, and I know you can do it.